You ever stop and wonder how you can change the TV channel from way across the room, or how you can hear a friend's voice on the phone like they're right there? Well, the answer is literally all around us. It's invisible, but unbelievably powerful. I'm talking about waves. They're the secret messengers carrying all the signals that shape our world, and today we're going to decode them.
Okay, so this might sound a little strange, but what if I told you that a simple ripple in a pond, the kind you see when you skip a stone, what if I told you that holds the key to understanding how your TV remote works? Seriously, it's the secret behind light, sound, even your Wi-Fi. Let's find out how that's even possible. All right, let's get right into it. To really get a handle on the complicated stuff, we've got to start with the basics. So first question, what exactly is a wave? And yeah, we're going right back to that ripple in the pond.
Okay, this right here is the absolute key. You have to get this. When you see a wave, you're not seeing stuff moving from one place to another. You're seeing energy on the move. Think about it. Imagine a little rubber ducky just floating in that pond. When the ripple comes by, what does the duck do? It just bobs up and down, right? It doesn't get carried across the pond with the wave. The energy moves, but the water itself, the actual matter, pretty much stays right where it is.
And here's a perfect way to see that exact idea in action. You can totally try this yourself. Just grab a string or a rope and hold one end still. Now, give your end a quick flick, just one little snap. You'll see this bump of energy zip all the way down to the other side. But, and this is the cool part, look really closely at any single spot on that string. It only moves up and down. It doesn't travel with the bump. That, my friends, is pure wave motion.
So, we've nailed down that waves are all about moving energy. Now let's dig a little deeper, because it turns out waves have kind of two main personalities, two totally different ways they get the job done. I love this analogy. Think of it as the wiggle versus the shove. So first up, we've got the wiggle. Let's go right back to our string experiment. Remember how the energy, that bump, moved along the string horizontally? But the bits of the string itself only moved up and down, vertically. See how those two motions are at a right angle to each other? That's what we mean by perpendicular, and that's exactly what a transverse wave is.
And because of that classic up and down wiggle, transverse waves have these features you've probably seen a million times. You get these high points, which we call crests, and these low points, called troughs. And yeah, light waves and those ripples on the water, they're basically the poster children for transverse waves.
Okay. Now for the shove. The best way to picture this is with a slinky. Imagine you've got one stretched out on the floor. If you give one end a sharp push forward, what happens? You see this pulse, this little bunch of compressed coils, shoot all the way down to the other end. Now think about it. The coils of the slinky moved back and forth in the exact same direction that the energy pulse was traveling. They're moving parallel to the energy, and that, right there, is a longitudinal wave. What's so cool about this is that you don't get crests and troughs here. Instead, that push-pull motion creates these zones where the particles get all bunched up. We call those compressions. And then zones where they're really spread out, which are called rarefactions. And the number one most important example of this kind of wave, sound itself. So let's put it all together side by side. You've got the wiggle, that's your transverse wave. The vibration is perpendicular to the direction of the energy, making crests and troughs. Think light, think ripples. Then you've got the shove, the longitudinal wave. The vibration is parallel, creating compressions and rarefactions. Think sound. See? Two totally different styles. But at the end of the day, they're both doing the exact same job, moving energy from point A to point B. Okay, awesome. So we know the two main types of waves, but how do we actually describe them? Like, how can we tell one wave from another? We need to dig a little deeper, because every single wave has a few core properties that act like its own unique fingerprint. First on the list is frequency. This is super simple. It's all about how fast a wave is vibrating. That's it. A high-frequency wave is just wiggling back and forth really quickly. A low-frequency wave is much more lazy and slow. The perfect example is sound. A super high-pitched whistle, that's a high-frequency sound wave. That deep rumbling bass you feel in your chest, that's a low-frequency wave. Next up, we have wavelength, and this goes hand in hand with frequency. If frequency is all about how fast the wave is wiggling, wavelength is about how long one of those wiggles is. It's the actual physical distance from one point on a wave to the exact same point on the next wave, so from the top of one crest to the top of the very next one. And here's where it all comes together in this really elegant way. Those two fingerprints, frequency and wavelength, are directly connected. A wave's total speed is just its frequency times its wavelength. It's that simple. And this one little equation, it governs every single wave in the universe, from the tiniest ripple on a puddle to the light that's traveled billions of years from a distant galaxy.
Okay, we've got the basics down, we know the different types, and we know their properties. So let's put all this knowledge to the test, shall we? We're going to use everything we just learned to compare the two waves we all experience every single day of our lives, sound and light.
Let's kick things off with sound. Now, the most important thing you need to know about sound is that it's a mechanical wave. What does that mean? It means it absolutely has to have stuff to travel through. It needs a medium, whether that's air, water, or even a solid wall. Sound is the literal vibration of particles. That's why, in all those space movies where it's totally silent during an explosion, that's actually accurate. In the vacuum of space, there are no particles to vibrate, so no sound. Simple as that.
Light, on the other hand, is a completely different beast. It's an electromagnetic wave. It doesn't need to bother with vibrating particles. No, it's this incredible self-propagating wave of electric and magnetic fields. It basically paves its own road as it goes, and that is why light can travel through the total empty vacuum of space. It's a truly amazing, fundamental property of our universe, and it's the reason we can look up and see the stars.
And if you thought they were different before, get ready for this. This is where the difference becomes absolutely staggering. Let's talk speed. In air, sound clocks in at a respectable 340 meters per second. Pretty fast, right? Well, light travels at 300 million meters per second. I mean, that's not even in the same league. It's a completely different scale of reality. It's the entire reason you always see the flash of lightning long before you hear the boom of thunder.
So, here's the final scorecard. You've got sound, a mechanical longitudinal shove wave that absolutely needs a medium. Then you've got light, an electromagnetic transverse wiggle wave that can cruise right through empty space. Honestly, their fundamental natures, and especially their speeds, could not be more different.
And you know what? All of this brings us right back to the very first thing we talked about. It doesn't matter if it's a wiggle or a shove, fast or slow, long or short. The one fundamental truth is always the same. When a wave is passed through medium or vacuum, we say that energy has been transferred from one point to another. At the end of the day, from a tiny whisper to a powerful sunbeam, it's all just energy in motion.
So there you have it. We started with a simple ripple in a pond, and from that we can now understand the invisible signals that power our entire modern world. I mean, we've pretty much mastered sound, light, and radio waves. But it really makes you wonder, doesn't it? What other invisible messengers are flying around us right now? What's the next wave we're going to learn to see that will change everything all over again?